Hello and welcome to my channel. My name is Pushpinder and today we are going to discuss about aromaticity. Now aromaticity is the property exhibited by benzene and other related compounds which differentiate them from the aliphatic compounds. Now these are the properties which are shown by the aromatic compounds. The first one is they have the high degree of unsaturation. It means that these aromatic compounds contains lot of double bonds in conjugation. Second is they are resistant to undergo addition reactions. Like in case of simple alkenes, if we take one simple alkene and we add bromine to this alkene, what we get? We get dibromo compound. We can see that bromine is getting added over here. So this alkene is undergoing addition reactions. But in case of aromatic compounds, these addition reactions are not followed in aromatic compounds. Rather, they undergo electrophilic substitution reactions. For example, if we have to add bromine to the benzene, then what would happen? This hydrogen will be replaced by bromine, and this hydrogen, this proton will have to leave its place. It will leave as HBr. So if the bromine has to add to this compound, to the benzene, then one of the atom has to leave from here. So this is getting substituted. This proton is getting substituted with bromine. So aromatic compounds undergo these kinds of electrophilic substitution reactions. Now electrophilic means, because if again we talk about bromine, here it can be written as delta positive and delta negative. This is the electrophile. It has electron cloud over here. It attacks to the bromine atom. Then the substitution of bromine takes place over here. So this type of reactions are called the electrophilic substitution reactions, in which electrophile is being attacked by the electron cloud. Now, the next property exhibited by aromatic compounds is that they have unusual stability. Like in case of benzene, you might know that benzenes are extraordinary stable compounds. They cannot be easily dissociated in simple conditions. They require harsh conditions to get dissociated. So they are extremely, or you can say they have unusual stability in their molecule. They are cyclic in nature, they are flat, or they are planar in nature. So these are some of the properties which are exhibited by the aromatic compounds. Now there are several theories which can tell you that whether any compound is aromatic or the compound is not aromatic. So one of them is the Huckel's rule. This is Huckel's rule. Now, according to Huckel's rule, a compound which is planar, which is cyclic, and also the pi electron cloud is distributed over all the atoms, and also the compounds which follow 4n plus 2 pi electron rule. These compounds are called the aromatic compounds. So on the basis of these rules, we will discuss some of the examples whether our compound is aromatic or not aromatic. So let us take first example, like in case of benzene. In this case, we already know that benzene is planar in nature. So it is following the first condition. It is cyclic. Following the second condition, pi electron cloud is distributed over all the atoms. We can see that these three bonds are they are present on all the 6 carbon atoms, like this, and this. And we write it as the resonance hybrid of benzene like this. So we can see from these structures that all the pi electron cloud are distributed over all the 6 carbon atoms. So this is also following the third condition. Now what about the last condition, the 4n plus 2 rule? Now what is this rule? In this case, if we put n is equal to 0, then 4n plus 2, we will get 2 pi electrons. If n is equal to 1, then 4n plus 2 will give us 4 pi electrons. If n is equal to 2, then 4n plus 2 will give us 10 pi electrons. Likewise, we have to see whether our compound has 2, 4, 10, and so on. These number of electrons, if are present in our compound, then the compound is following the 4n plus 2 rule. Let us see in case of benzene what is the case. Now, if we see that one bond is formed of 2 electrons. Now, here are we have 2 electrons. There are 2 electrons and there are again 2 electrons. The total pi electrons in benzene are 6 pi electrons. Now, sorry, here it was 6 pi electrons. So, now we can see that this benzene has 6 pi electrons. So this is following the 4n plus 2 rule. So in that case, we can say that benzene is following the Huckel's rule. That's why this benzene is aromatic in nature. Now let us take another example. Our next example is of pyridine. In case of pyridine, instead of carbon, nitrogen is one of the atom in this ring. Now nitrogen has one lone pair of electrons over here. Now uh, likewise benzene, this compound also has 6 pi electrons. It is planar, it is cyclic, and pi electron cloud is distributed over all the atoms involved in the ring. Now we are not going to count these 2 electrons because these 2 electrons are not contributing to the this ring system. So it has its orbital which is not in sync with the orbitals of this ring. So that's why we are not counting these 2 electrons over here. So we will see another example of pyrrole in which we will count these 2 electrons. You will get to know that whether where we have to count these electrons and where we don't have to count these 2 electrons. So in this case we don't need to count these electrons because these 2 electrons are not contributing to this ring system. Okay, so in according to this Huckel's rule, it also has 6 pi electrons. Okay, so this pyridine is also aromatic in nature. Now let us take some of the heterocyclic compounds. We have pyrrole, we have this furan, and we have thiophene. Now let us consider these heterocyclic compounds. Now let us take the first example of pyrrole. This pyrrole, this is cyclic, this is planar, and now we have to see majorly the 2 conditions like the planarity and the cyclic nature. We can easily see in the structure of the compound. We just have to see that whether the compound is following the 4n plus 2 rule, and also the compound in the system, the all the pi electrons are distributed over the all the atoms which are involved in the ring system. So in this case, we can see that here 1, 2, 3, 4, 5, 6. Now, in this case, pyrrole, we are counting these two electrons because in case of pyrrole, these two electrons are contributing to the ring system. Like we can write some resonating structures like this. These electrons will go over here. This electron will go over here. This is negative charge. This, we have hydrogen, one proton. Okay, now nitrogen is forming 4 electrons. It will have one positive charge. Now, these electrons will go over here and these will go over here. So, we can see that these are the resonating structures of pyrrole. We can see that all these electrons are distributed over all the atoms involved in this ring system. And here, these two lone pairs are also participating in the circulation of these electrons. So, that is the reason we are calculating it over here, that this is also the part of the pi electrons. Okay, so in this case, if we talk about the pyrrole, we can see that this is cyclic, this is planar, and this how many pi electrons it has? It has 1, 2, 3, 4, 5, and 6. It has 6 pi electrons. Okay, and also all the electrons are distributed over all the atoms involved in the ring system. So pyrrole is aromatic in nature. Similarly, we can explain about this furan and thiophene. Let us take the example of furan. Here we have furan. In oxygen, we have two sets of lone pair. In this case, again, these two electrons are contributing to the ring system, but another two electrons are not contributing to the ring system. Okay, so we will count only these two electrons over here. Likewise, in pyrrole, these electrons are also getting circulated over all the atoms. Here we have negative charge and oxygen will have positive charge. Now, these electrons will go over here and these will go over here. We have positive charge over here. Now, we can see that this is planar, this is cyclic, and it has 6 pi electron system, and also all the pi electrons are distributed over all the atoms involved in the ring system. So, this is the reason that furan is also aromatic in nature. Similarly, you can explain the aromaticity of thiophene. So, I am not going to explain it here because this is very similar to furan. Okay, you can do it yourself. Now, let us take another examples. These were the monocyclic systems. Now, let us take the examples where we have more than one ring in our compound. We have, let us say, we have naphthalene, we have anthracene, and the third example is, let us say, we have this phenanthrene. Okay. Now, in this case, This naphthalene has all these compounds are all of these compounds are cyclic in nature. They are planar compounds. Now we have to just see that whether all the pi electrons are distributed over all the carbon atoms, and another thing is that we have to see whether these compounds are following the 4n plus 2 pi rule. Okay, so let us see. It has 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. It has 10 pi electrons. This compound has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. It has 14 pi electrons. This phenanthrene is similar to anthracene because it has also 3 rings and the conjugated double bonds. It also has 14 pi electrons. Now let us see. Now we already know that all these electrons are distributed over all the carbon atoms. So we are not going to check about that. We will just see that whether these compounds are following the 4n plus 2 rule or not. Now in case of 4n plus 2, if n is equal to 0, then it was 2 pi electron system. If n is equal to 1, then it was 6 pi electron. If n is equal to 2, then we should have 4 to the 8 plus 2, 10 pi electrons. If n is equal to 3, then we should have 14 pi electrons. Okay. Now, from this table, we can correlate that this 10 pi electron and 14 pi electrons, all these pi electrons are following the 4n plus 2 rule, because when we put n, then we get the 10 pi electrons. When we put 3, then we get the 14 pi electrons. So all of these compounds are following the 4n plus 2 pi electrons rule. So all these compounds are aromatic in nature. So naphthalene, anthracene and phenanthrene, all the 3 compounds are aromatic in nature. Now let us take the examples of some of the um, anions and cations, like the um, now let us take the example of ionic compounds. What is the case in case of now let us take the example of ionic compounds, like the aromatic ions. Our first example is this 3-membered ring, in which we have one double bond over here, we have one H over here, and here is the positive charge. Let us take some other examples. We have H over here, we have negative charge over here, and we have double bond. Let us take neutral molecule also for the comparison. Okay, now in this case, all the 3 compounds are planar in nature. All the 3 compounds are cyclic in nature. Now, what we have to see? We have to see whether these pi electrons are distributed over all the carbon atoms or not. And the second rule, we have to find out that whether these compounds are following the 4n plus 2 rule. Okay, so let us see that how many pi electrons these compounds have. These have 1, 2. These have 2 pi electrons. These have 1, 2, 3 and 4. 4 pi electrons. This compound has 2 pi electrons. Now let us see, according to 4n plus 2 rule, which of the compound is following this rule and which is not following. So 2 pi electron is following 4n plus 2 rule, because if we put n is equal to 0, we get only 2. So 2 pi electron is following. Similarly, this compound is also following 4n plus 2 pi rule. Okay, this compound is not following 4n plus 2 rule. So we can straightforward say that this compound is not aromatic in nature. Now let us see another example. Let us see the another condition whether all these electrons are distributed over all the carbon atoms or not. Let us see. In case of cation, what happens? We have this positive charge, we have one electron. Now these electrons can move over here. We will get the resonating structure like, now double bond is here. This positive charge will shift to this carbon atom. Now if this double bond moves here, then this positive charge will shift to this carbon atom. Okay, now we can see that in this case these pi electrons are distributed over, they are delocalized over all the carbon atoms which are in the ring system. So this first compound is following both the rules. This is also following the 4n plus 2 rule, and this is also following the another rule that all the pi electrons are distributed over all the carbon atoms involved in the ring system. So this compound is definitely aromatic compound. This is not aromatic, so we will talk about third compound only. Let us see that in case of this third compound, we don't have any charge. We have only one double bond. Okay. Now, when we have only one double bond over here, there is no charge, then how these two electrons will uh, move to the another carbon atom? Like what is the which force will allow it to move towards the other carbon atoms? So these electrons are not moving to the other carbon atom. So this compound, this carbon is left for its the delocalization of now let us take the example of third compound. Now in this case what happens, that these two electrons are fixed over here. They don't have any motive behind to move around all the carbon atoms. So these two electrons, though it has 2 pi electrons, but these electrons are not distributed over all the 3 carbon atoms. So this compound is not following the complete rules of aromaticity. So this compound cannot be considered as the aromatic compound. So this is also not aromatic. This is not aromatic. Only this compound is aromatic in nature. Okay. Now let us take example of another compounds. Let us say we have this fine membered ring. We have negative charge over here. Again, we will take all the three cases: positive charge, negative charge, and the neutral one. Now, all the three compounds are planar, all the three compounds are cyclic. Now, let us see that whether the pi electrons are following the 4n plus 2 rule or not. It has 1, 2, 3, 4, 5, and 6. It has 6 pi electrons. It has 1, 2, 3, 4. 4 pi electrons. It has 1, 2, 3, 4. It also has 4 pi electrons. Now, according to 4n plus 2 rule, these two compounds are not following 4n plus 2 rule. Okay, because 4 electrons are not coming in any case in case of 4n plus 2. So, these two compounds are not aromatic. Now, let us see this compound whether all the electrons are distributed on all the carbon atoms or not. We can see the resonating structures over here. It can go like this. Now double bond is here, negative charge is here, double bond is here. The negative charge will go over here. Now we can see all the resonating structures of this 5-membered ring. We can see that all the electrons are distributed over all the 5 carbon atoms. So the first compound is following all the rules of aromaticity. So this compound will be aromatic in nature. So we can have you can also discuss. Let us take the third example. Let us take third example of cycloheptatrienyl cation. We have positive charge over here. Like other two examples, we will consider both the cases. Sorry, we should draw it like now. In this molecule, we have 6 pi electrons. No, here we have 2 more electrons. We have 8 pi electrons. We have 6 pi electrons. Now, according to 4n plus 2 rule, which of the compound is not following 4n plus 2 rule? This is following 4n plus 2. This is also following 4n plus 2, but this is not following 4n plus 2 rule. So, the second compound cannot be aromatic in nature. Okay. Now, let us see the compound number 1 and compound number 3. This was compound number 2. 2 is not aromatic. Now, let us compare 1 and 3. Whether all these pi electrons are distributed over all the carbon atoms or not. Now I will not draw all the resonating structures. We can see it from here only that these electrons will go over here, these will go over here, and this will go to this position. So this way these electrons are distributed over all the carbon atoms. But in this case, this carbon is not contributing to the circulation of these pi electrons. These will be circulated only to these carbons only. So this carbon will be left behind. So this carbon is not participating. So all the carbon atoms are not participating in the circulation of these pi electrons. So this is the reason that this compound cannot be considered as the aromatic compound. Only this compound is aromatic in nature. So I hope now you can compare all the compounds whether uh, these compounds are aromatic or not, because in exams these types of questions are asked where all the cations, anions and the neutral compounds are compared, and you are asked to tell whether which of the compound is aromatic in nature, and you have to explain that which that what are the reasons that which one is aromatic, which one is the aromatic compound and which is not the aromatic compound. So I hope you like this video. In our next video, we will discuss about the aromatic, anti-aromatic and non-aromatic compounds, and also we will talk about the annulenes in our next video. Till then, goodbye.